Greetings, ladies, gentlemen, and anyone in between. My name is Christopher Markor, but today you may call me Dmitry Mendeleev, because today we are talking about the periodic table. Now, what we're going to be covering today is going to be the basic information about the periodic table, like what's on it, and some things that relate to it, like isotopes and charges and stuff like that. So if you don't already, I recommend getting a periodic table for yourself so you can take notes if you are planning on using this to study for some reason. If not, then I guess you can still take notes on your own, but this will make it much easier. Or if you're just listening this to learn a bit more, then that's fine too, nerd. So let's start with the basics of what is a periodic table. It was created in 1869 by some guy called Dmitry Mendeleev. I don't think you've heard of him. Basically, it was designed to categorize the elements. Before then, there were so many different ways to organize them, but none of them really fit. But the periodic table was designed so that not only was it based on atomic number and atomic weight, but also designed on how they connected to each other, they were in different design. Give me a second, sorry. It was basically designed to show the properties in different columns. There we go. I'm not cutting that. Yeah, that, and in fact, because of this, it was so good that it was even used to predict three different elements: scandium, gallium, and germanium. Gallium, in fact, is the main example I heard about this, because he predicted almost perfectly. So then, why don't we begin? So we did with how the periodic table is organized, that being in rows and columns. But we don't really use those words when it comes to the periodic table, because we like to be fancy about our words, because why not? So we use different words. For example, when it comes to a column, we use group, which makes sense considering the fact that that's kinda how groups are. Elements in the same group will share several different similar properties. But rows, now this is a part of chemistry I'm sure most women will hate, and that is the period. You know what, I'm going to keep that in. Stupid joke, but I don't know, I kinda like it. So let's go on to the basic parts of the periodic table. Now, there's a chance the one that you have is a little different, but every one I've seen has at least this: the atomic number. For those who don't know, this can be used to represent number. The element symbol. Sorry, I'm going crazy a little. I swear I've been hearing weird noises. Anyway, element name, and standard atomic weight. Okay. So let's discuss, what each of these means exactly. Atomic number. Basically, it's the number of protons. It truly is as simple as that. Maybe there's a different explanation, but if you know the amount of protons, then you know the number. If you know the number, you know the amount of protons. That is the easiest way to remember it. Really. Element symbol. Do I need to explain it? It's basically just the letter or letters used to that are assigned to its element. For example, F is fluorine, Au is gold, Fe is iron, Si silicon, and so on. As you can see with like gold and iron, they don't use the English words. I know for iron they use, I believe, Latin, or they might be Greek. But yeah, they use different languages for some of this. That's why tungsten is a W instead of a T. I have no idea if my cat's under my bed or not making that noise. I don't know if you can even hear it, so sorry. Element name. It's the name of the element. I hope that helps. Depending on where you are, you know, it's probably going to be a little different, but I'm currently going to go over the English name, using the English name, so I hope you don't mind. Lo siento. And then a standard atomic weight. Now this is a bit more interesting, and basically it is how much a unit of it, a mole of it weighs around there. And and the main way to calculate it is basically adding up protons plus neutrons. Electrons do not count. The reason why is because let me give you a good example. Let's say a proton weighs 1. Let's just set that standard, right? It weighs 1. What unit? Any unit. Just say 1. Neutrons weigh about the same as a proton, so we will also simplify that as 1. But electrons, they're so small, even when compared to protons and neutrons, that you don't really count it in the weight. And that's why it's weird, really. Just know that protons plus neutrons is weight, electrons do not matter in that regard. Alright, now that we've gone over that, let's go over some more element-based things that still connect to the periodic table. So why don't we begin with something simple? We've talked about neutrons, protons, and electrons a bit, so why don't we go over what exactly it means for an element and how changing those things around will affect them. So for example, add or remove a proton per se. What this is going to do is turn it into a different element, basically. So for example, let's say I have beryllium, number 4. If we add a proton, it becomes boron, but if it loses a proton, it becomes lithium. So yeah, protons are very important. That's why when you're doing practices with weights, you never change protons, because protons are what makes an element an element. So you can't exactly make lithium heavier by adding protons. That's just going to turn it into beryllium or boron or more. Next up, adding or removing electrons. It changes the charge of an element. For example, let's go with magnesium. Add 1, it becomes magnesium plus -1. Yeah. By adding an electron, you make it more negatively charged, so you get -1, although it's mostly simplified to just a minus sign. When it comes to just 1, if it were more, then you would actually put the number. And which means that if you remove an electron, it becomes magnesium plus 1. You'll probably see a lot of exercises about that, and mainly on how oxidation numbers work and stuff like that. We might give me a second. Okay, yeah, I'll do explain it later, so we can go more in depth on that in a bit. Now let's move on to adding and removing neutrons. Now neutrons don't really provide a charge or anything like that, so moving them and adding them instead changes the weight. It's hard to explain like this, so why don't we move on to, something to the main example of how neutrons affect things, and that's with isotopes. Now, what is an isotope? Well, an isotope is basically a type of element. My apologies, I'm thinking. Basically, different elements of different weights because they have different amount of neutrons. Now, some elements don't have isotopes. For example, gold only has 197, or at least that occur naturally. That's why if you go to your periodic table, you'll see that the weight of gold is almost 197. It's very close. The only difference is by 0.03. That because this is the main one that can be found in nature, and by main I mean basically only one. Most other isotopes of gold are man-made, but still they average out somehow they average out and get 196.97. Now the interesting thing comes when there's more than one prevalent isotope. For example, carbon. Carbon has carbon 12 and carbon 13. I forgot to explain that. My apologies. Basically, when writing out an isotope, you write the element name, dash, and then the weight. I'm so sorry for not explaining that earlier. So, I'm getting off track, I'm sorry. Let's continue on with what we have. So, now we're going to be asking ourselves how common these two are. Well, simple. I actually have the numbers right here. If you are ever in an assignment and you are tasked with doing something like this, you are either going to be given the information, or you are going to be allowed to look up the information. You are not meant to memorize how prevalent these things are. The only thing you need to focus is remembering the equation. So first let me show you the percentages and then we can move on to the equations, are we? Okay, so this is 98.9% and this is 1.06%. Is that really correct? Yeah. If you're wondering why it doesn't go up to 100%, that's because there's technically other isotopes that kind of count for. They are so rare in nature that they're basically just man-made. Same thing applies with gold. I just explained it poorly back then. So the equation to do is simple. Since we only have two, it's going to be really simple. We just, let's see, 0.989 times 12. Now, if you've taken statistics, you probably know this, but what a percentages don't actually look like this when you're using them for math. This is just how we simplify them to make them easier to understand. When writing them out for mathematics, we divide this by 100, or if we want to simplify, we multiply this by 100. So yeah, that's 0.989 times 12. Is it multiply? No, it's done plus 0.106. Oh no, that's wrong. My apologies. That's 0.106 times 13. And that over the amount of isotopes found in nature, which in this case are just 2. We can ignore the others, don't worry too much about it. And if we do this math, you're going to get around 12.01, which is the atomic weight that you find on the periodic table. So that's the type of equation that you are going to end up doing. So yeah, I guess I should quickly go over another way to show isotopes, and that's by this symbol. So we were talking about carbon. Okay, so we have this. Now this is the number of protons and this is the weight. Yeah. So if you're given this, not only do you immediately get the element and the amount of protons, but also the weight, and therefore you can get the neutrons, because 2 to the minus 6 neutrons and 6 protons. So I prepared a bit more, but you know. Next up, charges, right? So why don't I explain how charges work? See, electrons have preferences in how many electrons they have. Well, not exactly how many they have, but how the electrons are organized. So let me give you a simple example. Nitrogen. It has one cell, 1, 2, and a second. Hi, Cookie. It was my cat after all. Here it is. Anyway, so nitrogen 1. Okay, so as you can see, this nitrogen has 2 inner electrons and 4 electrons in what we know as the valence shell. What this means is basically the outermost shell. Now, the thing about them is that they're very picky about their valence electrons. They want a full balanced shell. So how can they get those? Well, simple. They can either gain electrons or lose electrons. So for example, let's say this nitrogen wanted to gain electrons, then it would add 1, 2, 3, 4, and bam, a full shell of electrons. And now it's happy and has a charge of -4. But what if it doesn't want to add them for some reason? Maybe it's trying to bond with a negatively charged atom, so it will make sense for this one to also be negatively charged. Then it's going to lose electrons, and basically it's going to lose all 4 of the balanced electrons, and now it has just one full cell. Now the first shell can only have a maximum of 2. That's why this only has 2 and yet is considered full, and also has a charge of 4. Now you may be wondering, how do we know if an element it gains or loses electrons? Well, it's simple. Electrons are like us. They're lazy and they are going to do as little effort as possible to get what they want. Now for nitrogen and elements under it, like phosphorus, arsenic, antimony, I'm so sorry, bismuth and moscovium, they can choose to be negative or positive, but most others have a preferred option. For example, let's go with beryllium. Now, beryllium has the option of either gaining 6 electrons or losing 2 electrons. Now, which will it choose? Well, it's going to choose to just lose the 2 electrons, you know. It requires much less kinetic energy to remove those electrons, and you'll still have a balanced shell after it. So it's going to obviously choose to just remove the outer 2 electrons and gain a +2 charge. But what if it wasn't beryllium and it was oxygen? Now oxygen has 6 outer electrons, so now it gets the option of either adding 2 electrons or losing 6 electrons. And of course, it's going to choose to add 2 electrons because it takes less energy. Now, there might be times where they don't do that, but that's under very, very strict circumstances that will not appear in nature, and therefore you will not have to worry about while studying. So trust me on this, you won't have to worry about it. Let's see what else. Oh, that's all I have for today, it seems. Well, I hope you enjoyed today's video. I'm sorry for the long wait. I just put too much pressure on myself for a week for a video, even 2 weeks. Like, I still need to get a passion for video making. It makes no sense for me to ruin it by making myself hate it. So this video took, I believe it's been 3 to 4 weeks. So yeah. And the next one is going to come out in time. I won't worry about it taking like more than a month, but I'm not going to make any promises. Yeah, but I hope you enjoyed, and thank you for staying to the end. I'm a little worried that no one's going to get to even 10 minutes, because on my last video that I'm proud of, the main watch time was like 5 minutes. So yeah. I certainly hope that you were able to learn something or found something interesting. If you have any questions about this subject, leave them down below. If you have any questions that are not part of the periodic table but you still want solved, then let me know, and I might make a video on it. I don't have a topic yet for the next video or find inspiration. Although there's a chance I might not be chemistry related. I'm currently not taking any chemistry class, so who knows if I decide to make a statistics or trigonometry video. Because of those are the 2 main classes I have, and they do interest me, so we'll see. So yeah, I don't know, go watch a good YouTuber like Bringer or something. Bye.